Hello physicists, this is the Introduction to Thermal Physics topic, and today's lesson is also an introduction to an aspect of thermal physics called kinetic theory. Kinetic theory we will revisit after the thermal physics lessons coming up later this week. So today is really just an intro to what we mean by kinetic theory. This image of a cup of tea here wasn't there by accident. If you've made a cup of tea, and I'm sure a lot of you have, you'll know that you should use boiling water. And if you were to try and make a cup of tea with cold water, you'll notice that if you put a tea bag in cold water, you'll barely see any change in colour of the water at all. Now that's an observation. I'm going to be using the term observation quite a lot in the lesson. That's an observation, but it doesn't really explain anything. It's just what we notice happening, that different temperatures affect the way the tea mixes with the water. And if we look at this little example here we've got 3 jam jars at different temperatures, and in each one some food colourings being added. This is a similar idea to the cup of tea. That the food colouring mixes quite quickly in the hot water, but less so in colder room temperature and then actual cold water as well. So some of these observations are interesting, but it's very difficult to know what's going on. And in fact, only about 115 years ago, 1905, was there really clear evidence of why this was happening. Lots of scientists had speculated on the idea of molecules and particles that make up matter, but there was no direct evidence. So this lesson is really going to look at what was it that enabled scientists to be more confident about the existence of particles. In addition to water mixing and liquids mixing, we all aware of the fact that we can smell things even if we're not nearby to them. And you can make a cup of coffee in the morning. I know if I make a cup of coffee downstairs, other people in the house know it's been made long before they come downstairs, and it's not necessarily because there are drafts of air taking the smell around the house. It's because of what we call diffusion, and that's what's happening in the liquid. Now diffusion could just be explained or describing the actual spreading of the smell, but actually now we have a much better understanding of what it is and why it happens, and so kinetic theory is going to help us with this idea. So what do we mean by the kinetic theory of matter? Really, it's a model that we are going to use to explain the properties of matter. This doesn't just apply to diffusion, the spreading or mixing of gases and liquids. It's also to do with explaining how it is that the way solids, liquids and gases behave, and how they are different from each other in terms of their particle makeup. And then we'll also be looking at what happens when matter changes phase, which means when it changes from, say, solid to liquid, or liquid to gas, or gas to plasma. There'll be lots of transitions that can occur, and how do we explain that in terms of kinetic theory? A lot of this, in fact most of it now, is based on the work that was done by Einstein in 1905, who in turn founded his theory of particle motion on an observation by a botanist, Robert Brown. And this so-called Brownian motion, which you'll see examples of in the lesson, enabled Einstein to conclusively say that there must be atoms or particles causing this motion. So up until 1905, although lots of scientists had speculated on particles, there was still quite a lot of skepticism that they actually existed, and it was Einstein's work that confirmed the existence of small particles that cause this Brownian motion. Just going to drag down the top of this table because that's a little bit, I don't know if you can quite see that there. We've got microscopic quantities, and we've got, just going to drag that up there, top microscopic quantities and macroscopic quantities. So we're going to be looking at two scales. On the kinetic theory very much looks on the left-hand side at the microscopic quantities. So it's looking at the underlying causes, what actually is going on at the particle scale, and we'll be looking at speed of particles, the mass of particles, and the number of particles in order to explain some of the macroscopic properties, quantities that we know quite well. So things like pressure, temperature and volume, we know how they are related to each other through the gas laws, but until kinetic theory came along, it wasn't possible to say why the pressure changed in a way it did when temperature changed. So there were good relationships that had already been discovered between pressure, temperature and volume, but the underlying physics wasn't known. So kinetic theory is so important because it establishes the cause of these changes. One of the things that is quite different about this topic is that we are talking about vast numbers of particles, all moving at different speeds. How on earth could we possibly come up with a model or a mechanics model that would take into account every single particle so we'd know what the overall effect would be? And really we can't treat this type of work in the same way. We are going to be using what we call statistical mechanics. Statistical mechanics is taking large numbers of, let's move my little camera view out of the way there, large numbers of particles and averaging their speeds and treating them in a statistical way rather than individual particles. So that's at first seems very difficult because we can't see what the particles are doing very easily, and yet we can still come up with some very clear ideas about the pressure that would be caused by a volume of gas. So it's quite an interesting bit of physics. It's slightly different to the way we've done mechanics before, but I think you'll all find it pretty interesting. Okay, thank you.